Let's continue our lecture. I'll try to finish everything by 9:30. Okay. So non-linear implicit equation. So here, the question we're facing is a nonlinear implicit equation in the sense that the Black-Scholes formula, even though it's a closed form formula, but it's implicit in the sense that we cannot rearrange it to isolate the volatility term and rid of the value right away. Because you see, volatility is hidden inside that D1. And we have that n function, cumulative density function there. It's a nonlinear function, okay? Essentially, even though we know that this equation has a unique solution for sigma, okay? But we cannot rearrange it and isolate sigma. So that means we cannot solve sigma directly. It's an implicit function. Okay, we have to use some numerical techniques to solve, to get the solution for sigma. Okay. Now, so here our target becomes we want to find a sigma star that makes C sigma star minus V equals 0. Here, this V is the market is the observed option value from the market. This V is the observed option value from the market. Okay. So now we look at this nonlinear, how to solve a nonlinear implicit equation. Okay, let's look at a general problem. Okay, so given some continuous nonlinear monotonic function f(x), we want to find a real number x star such that f(x star) equals 0. So here, this f star put into the context of this problem, the f star will equal c sigma star minus, so c x star minus v. Okay, so this is our equation. Okay. To solve this nonlinear equation, okay, there are several choices we can make. Okay, the first one is we can use guesswork. Okay, we just guess. And the second, apparently, if you just random guess, it's really low efficient, right? Highly non-efficient. So what do we do? That we use inspired guesswork. So use our previous guesses to make new, better ones. So the first method actually is the bisection method. So this is the most straightforward method to solve a nonlinear implicit equation. Okay, so let's say, given this nonlinear equation, implicit equation, we can make two guesses. The first guess is xa, and the second one is xb. Okay, and the only requirement for A and B is that they satisfy the condition fxa times fxb is negative. You see, our target is to find a solution f(x star) make the function equal 0. Okay, now we found two guesses, one is xa and one is xb. Then the value of the function on these 2 points have opposite signs. So that means the product is negative. Then we know that if the function, the nonlinear function fx must cross 0 somewhere in between xa and xb. here we rely on the previous condition is that the fx here is continuous nonlinear monotonic function. That means either is goes up with x and goes down with x. Is on the same direction. It cannot oscillate. It's a monotonic function. Either it's a decreasing function or decreasing function with respect to x. So that whenever we have two guesses, but the option value have different signs, we know for sure that the 0 point, the x star will fall in between this A and B. Okay? Then we use the divide and conquer approach to find the x star. So let me show you this approach. In detail. So here is the bisection method. Okay, the steps. The first step is find xa and xb with this. Okay, such that they have different signs. We don't need to know which one is positive and which one is positive, negative. It doesn't matter. It depends on the function itself. But as long as they have different sign, that satisfies our requirement for bisection method. So once we found these 2 points, xa and xb, we take the midpoint and evaluate the option value or the function at this midpoint, x mid. Then we check if x mid becomes 0, oh, this is the right solution we're looking for, right? Then stop. Now, if the sign of the midpoint, the sign of the option value at the midpoint, and one of the endpoints, xa, let's say, are different. So that means essentially their products are negative. Then we reset xb to x mid. Essentially, we know that the true solution will fall between a and the midpoint. Otherwise, we know that the midpoint will fall in between the mid and the xb. Essentially, we keep on refining the range for the possible solution. Essentially, we'll reduce the range. Every step, we have the size of the possible range for the true solution. Okay. So whenever the distance between the A and B, the two endpoints, is less than a given epsilon, a given threshold, okay, then we stop and use the midpoints as the approximation for the true solution, okay? Otherwise, we go back to step 2 and continue to refine the range, okay? So note that here we must choose a value, a threshold beforehand for our stopping criteria. Okay, so that means the tolerance of your accuracy. So I mean, what's the tolerance of the error is. So once you decide your tolerance for the error, then you can repeat the steps until you reach this accuracy. Okay. So the approximation error is guaranteed to be no more than half of the given tolerance. Okay, so this is the bisection method. So bisection method is by far the most straightforward method for solving nonlinear implicit equation. But there are some tricky stuff with this bisection. First of all, there's no foolproof procedure to finding suitable xa and xb. So that means it's not, there are no guaranteed method to easily find xa and xb that have the different value, different signs when you apply the option function to these 2 points. Okay, so normally we just pick up 2 points that are far away from each other. Okay, as long as they're far enough, they should be able to satisfy this condition. Okay, So without specific knowledge of the function, then we must restore to try and error. Essentially, you pick up 2 points that are far away from each other and check whether the value on these 2 points have different signs or not. Essentially, just a try and error. Okay. Actually, this is not the most tricky thing for bisection. The tricky part is that this bisection method is not very efficient in finding the true solution. You see, because every time you check the sign of the 2 endpoints, then you take half, then you take half, then take half. So each time, if at the very beginning the 2 points are too far away, it needs you to take many different steps until you be able to reach the given tolerance of error. Okay, so this bisection method has linear convergence. So that means each time the error reduced by half. Okay, because every time you check the sign of the values on those 2 points, you reduce the range by half. Okay, so that means each time the error reduced by a linear factor half. So it's a slow method. Okay. In engineering, most of the time we don't use bisection, even though it's straightforward. We use Newton-Raphson method, okay, or simply called Newton method. Okay. Now, the Newton method starts with a guess as well. Okay, let's say we have current guess Sn. Sn here, this is the guess we have obtained at step n. So the subscript n here means step n. Okay, let's say we already reached the step n and we got approximation xn. Now let's see how we move to the next step, xn plus 1. So here we assume that fx is differentiable, and we write epsilon n equals x star minus xn. So x star here is of a true solution. We don't know the true solution yet, but let's just use this notation. We use epsilon n to describe the current error of xn. Okay, xn is our current step n approximation from xn, the n step. So then the Taylor series expansion tells us 0 equals fx star, right? This is the implicit equation we want to solve. And x star equals fxn plus epsilon n, right? Because we use epsilon n as our pricing error, right? Then we apply the Taylor expansion, fxn plus epsilon n times f prime xn plus epsilon n squared divided by 2 f double prime xn, second derivative. Okay. Now, if we ignore this second order term, okay, apparently this term is high order of epsilon n, right? Then we get epsilon n can be roughly approximated by this, because if you remove this term, essentially these two terms equal 0. So you can solve for epsilon n here, okay, which is fxn divided by f prime xn. Take the minus sign here. Okay, so once we know epsilon n, then we know x star can be approximated by xn minus this term, right? Because this is, you see here, x star equals xn plus epsilon. Easy epsilon is this guy. So x star can be approximated by xn minus this. So essentially, this approximation tells us if we already have the approximation from the current step n, which is xn, we can get the approximation for x star by this expression. And this expression coming from the Taylor expansion. And when we apply Taylor expansion, we ignore the second order term. So x star with this. So with this estimation, we can get our next guess. So xn plus 1. So the approximation for the true solution at the next step, n plus 1 step, will just be xn minus xn divided by x prime xn. X prime here is just the derivative with the derivative of the function with respect to xn. Okay. You see here, this is how we look at the Newton method, Newton-Raphson method. So this is the derivation of Newton method. So why we do this? Actually, this approximation coming from the Taylor expansion. Okay. I forgot to mention. So this is only for information only. So you don't need to derive this Newton method. We never ask you to derive Newton method. You only need to know how to implement it. That's it. Okay. Because this is part of your second assignment, you're going to implement this Newton method yourself. So to see how quickly the error decreases, let's go back and look at the Taylor expansion. So here, I want to compare the error at the current step and the error at the next step. I want to compare the error at the next step with how quickly it can reduce from the current error. Okay. So here is another approximation calculation. So essentially, epsilon n plus 1, this is the approximation error at the next step. It becomes is x star minus this. Okay. And x star, previously we know that the x star minus xn, this xn plus 1 equals xn minus this term. Now x star minus this one, then plus this one. Okay. Now x star minus xn, this is just the pricing error, the approximation error at the current step, n step. Sorry, the step n. Okay. So that means epsilon n plus 1 equals n plus this term. Now, if you look at the Taylor expansion previously, this term, you put this term back, okay, because we ignored it. Whenever you put it back, then we end up with this term. So what does this mean? So that means, you see, the approximation error at the next step is proportional to the second order to the power of 2 of the current pricing error. Let's say if the current error is 0.1, let's say, then the next approximation error at next step will become 0.001 because 0.1 times 0.1 is 0.01. Okay, that means the magnitude of the pricing error approximation at next step is reduced. Okay. So if we assume this constant by 1, then the new error proportional to the square of the old one. Okay, which means the Newton-Raphson method has second order convergence. Okay, but in the derivation here, whether it's this one or this one depends on Taylor expansion, right? So Taylor series expansion, so the requirement for Taylor expansion is that the pricing error itself is small enough. This is the necessary condition for Taylor expansion. So if this is too big, this simply doesn't hold. Okay? So that means as long as the initial guess you made for Newton method is close enough, the initial pricing error is small enough, then we can use the Newton method and quickly achieve our given approximate accuracy. Okay? Let me give you an example, a couple of examples for Newton method. Then we talk about the Newton method for implied volatility. So the first one, given a positive number A, can you find 1 over A, the reciprocal, without doing derivation? Actually, this is a very typical quantum finance interview question. I got asked about more than 15 years ago when I was looking for a job. Okay, so here I just write it down as an example for Newton method. Okay, there are many different ways to solve this problem using Newton method to find the reciprocal. Okay, you said here I just choose fx equals 1 over ax minus 1. I mean, you can choose any other form of function as well. But either way, so you just apply Newton method, get the formulas for each step. Okay, how do you refine the approximations from the current approximation to the next step? Okay, the second question is find the square root. Given a positive number, find the square root A. This is another interval question. I'm not sure whether now this question is still got asked or not, but 15 years ago, this is very popular. Just want to test whether you know or you're familiar with the Newton method or not. So this is 2 examples. I mean, I've written the formula here. You can write a simple short piece of code and test whether you can easily find the solution for these 2 numerical questions. Okay. So now let's look at some general observations regarding Newton method. Okay. So Newton method will normally converge very quickly, okay, roughly doubling the number of decimal places of accuracy at each iteration. For example, if the current step, the current approximation has, let's say, 3 digits of accuracy. So that means it's accurate up to 3 digits. Now, the next step normally goes to 6 digits. So that means each step will doubling the number of decimal places, okay, at each iteration. Then you think about it for the compared to the bisection, it's much, much faster, okay? But sometimes it fails to produce this kind of convergence if the true solution is 0, have 0 values for the derivative. So f prime x star equals 0, then this Newton method fails. So you see, for this nonlinear function, let's say x cubed equals 0. For this nonlinear function, if you apply this to apply Newton method, Newton-Raphson method to solve this nonlinear equation, then you're gonna fail. Why? Because f prime x star equals 0. The x star just 0, right? So f prime x star equals 0. So when you look at the update iteration function here, the f prime xn is in the denominator. So that means you're getting closer to the true solution. This is getting getting closer to 0, which makes this the updated term becomes huge. Okay, so that means the x_n plus will oscillate up and down, and never converge. Okay. So Newton methods fails for some cases. In some cases, it fails. And also, Newton method requires a suitable initial guess. The suitable here means the initial guess has close enough to the true solution. The accuracy, the error, approximation error from the initial guess has to be small, so that we can apply the Taylor expansion, so that we can get the more accurate results based on the adjustment from the current step. Okay, so given this two observations, it's always a good idea to do a sanity check on the results. So let's say you use Newton method to solve a nonlinear equation. Once you get the true solution, once you get an approximation for the true solution, it's always a good idea to put the approximation into the original nonlinear function to check whether you really get results close to 0. Because sometimes you may end up with oscillated results, but you didn't know. But when you put the approximation results from your Newton method back to the original nonlinear function, you will see whether the results of that nonlinear function with this approximation close to 0 or not. If it's far from 0, that means you get completely disastrous approximation. You should discard it. Okay. Bisection method can be used to generate a good initial guess. So because bisection method at least guarantee you can find a true solution. Okay, but it's slow. So what you do is you can start with bisection, then at the middle of your bisection, then you just stop bisection, then using the approximation from bisection and feed into the Newton method, then start work with Newton method, and so that it can get faster converged approximation. Okay. The last point is just a paper for your information. This is a paper that is a 2-point Newton method, suitable for non-convergent cases and with super quadratic convergence. So essentially is an improvement to the classic Newton method. So for your second assignment, okay, you are asked to calculate the implied volatility with real market data. I can tell you now, you will have some trouble dealing with the real market data using Newton method. There are several points you should pay attention to. First of all, don't blindly plug the option value into a implied volatility solver. So don't blindly try to solve for implied volatility given any option prices. First thing first, check whether the option prices is reasonable or not. That means whether the given option prices have arbitrage opportunity or not. We talk about the possible arbitrage opportunities, right? So we talk about the inequalities, we talk about the put-call parities, we talk about the upper bound and lower bound. First of all, when you pull out the real market data, first check whether there are obvious arbitrage. If the option price themselves commit arbitrage, that means violate the arbitrage relationships, then you shouldn't bother to calculate improbability, because by no means you can get any improbability from option price with arbitrage. Okay, so the first thing first, check whether they're arbitrage. If the option price itself is not reasonable, you output NA directly for the improbability. You don't need to calculate the improbability in that case. So then here is another reminder that in the real market, there could be possible arbitrage opportunities. Okay, so don't blindly calculate the improbability without checking. Okay, this is one thing. Second thing is that when you deal with the real market in second assignment, when you get the improbability, see whether they give you 0 when you plot back into your nonlinear function. But similarly, you need to do a sanity check on the approximation you get from the Newton method. I'm pretty sure there are oscillations. Okay? There are oscillations. You didn't, simply the approximation doesn't make sense. Also, the improbability should be always positive. If you start to see negative approximation, that's wrong. You should stop right away. This also implies that actually there are some problem with the input data. Maybe it's the option price itself has issues. Okay. What else? The third one is you can try this paper. If you want. It's not a part of the requirement of the assignment. The reason I put it here because every year there are some students that ask me, they see oscillations, they come to me, they ask me whether I have any suggestions. Normally I just give them this paper. It helps a bit to improve the calculation, okay? But you don't have to do this. It's not the requirement of this work, just simply for information only. What else? I think that's it for the second assignment. Now here I give you the code, the Python code I wrote for calculating improbability using Newton method. Pretty much you just copy and paste, okay? But you need to do the sanity check yourself, okay? Here is the code. We're going to talk about this. But I give you the code here. You can copy and paste. But all the points I just previously mentioned, check the option prices, sanity check when you get the improbability, and make sure that the improbability is never negative. All these ones you have to take care of them yourself, okay, in your program. So let's look at how to calculate improbability using Newton-Raphson method, okay. So our target is to solving the improbability given these 4 items, right? Current spot price, strike level, risk-free interest rate, and the time to maturity, and also the option value. Okay, so the nonlinear function itself is just C sigma minus v. Okay, so the option function minus observed the market value. Okay, this is our implicit function. Okay, and equals 0, then this is an implicit equation we want to solve. Okay. Now we write this. Okay, that will be our definition for the nonlinear function. And here I give you the derivative of this function directly. So the derivative of this function with respect to sigma is this. Okay, you can directly use this expression. You don't need to derive yourself. Okay, so we need f prime sigma in Newton method. So here is the expression for this term. Okay. Now also I give you the initial guess. So note that f prime greater than 0. So f sigma is monotonically increasing with Rexel sigma. So that means whenever the implied the volatility term goes up, the option value goes up as well. Okay, for call. Okay. So f prime is monotonically increasing with respect to this. So limit of this. So that means when sigma goes to 0, that means implied volatility goes to 0, we get this. When the volatility goes to infinity, the call option value becomes the current spot level. Okay? So this is two observations. Then based on this, we can get the initial guess. Okay, we don't need bisection method to find the initial guess first when we apply the Newton methods to solve implied volatility. So here, because if V fall in between this range, there will be a unique solution. So essentially here I'm telling you, whenever you load the market quote from the data file, you should check whether the European call option fall in this range or not. If it's not, that means the option value is not a valid quote. It's not a valid quote. You cannot solve for implied volatility. Okay? So this is the range you should check for European call. You should be able to derive a similar upper bound, lower bound for European put. Okay, here I'm talking about the European call. You should do similar thing for European put yourself. If you cannot figure out the corresponding range for European put, send me emails. Okay, I'm gonna give you the derivation. It should be straightforward, very similar to call. You get to give it a try. If you couldn't, just send me email. Okay. Or maybe I put in. I'm not sure whether I put it in the assignment. Let me see whether I put it in the assignment. Oh, I didn't. Probably I should. Anyhow, so if you don't know, then send me email. Okay. Now, so the first step when you calculate implied volatility, you should check whether the option quote, option value V is a valid number or not. Once you've done that, if it's falling in this range, then we know, oh, it's a valid number. So we should be able to get the implied volatility based on this quote. Okay. Then from the Black-Scholes formula for European call, I derive this. Okay. Now because partial C, partial sigma is maximum over this at this sigma hat. So here, sigma hat will be our initial guess. Okay. This will be our initial guess. Now once we have the initial guess, okay, we will be able to have the complete Newton-Raphson method for implied volatility. Okay, here I explained why sigma hat is a good initial guess. You can go over the derivation here. I just skip it. Okay, if you want to know, you send me emails. Okay, to save some time, we just skip this mathematical derivation, okay? But it's good to read this derivation if you have time and you have the necessary mathematical background. It shouldn't be too difficult. It's similar to the derivation for Newton method, okay? But either way, we're starting with sigma hat, okay? Here is the Python code. Now, here, let me explain this part. Import Black-Scholes as BS. So this Black-Scholes actually is just the implementation of the Black-Scholes formula, okay? My implementation of the Black-Scholes formula. If I remember correctly, you can also install this package. I think that somehow some people implement this, but you don't use this package for the first question. I ask you explicitly you to implement the Black-Scholes formula, okay? I want you to implement the Black-Scholes formula yourself and do the analysis yourself so that you get more familiar with Black-Scholes formula. So here, I implement myself, but previously some student told me that actually you can load this package somewhere. It's a third-party Python implementation package. But anyhow, I just remind you, don't do it for your first question, okay? So we have this R, we have this is the given parameters. Now here, this R is 3%, S is 2, that means the current spot level is 2, and strike K is the strike level, and time to maturity, the current time to maturity is 3 years. And sigma true here is 0.3. The European type is called. So sigma true here, what's sigma true? Sigma true is, because you see here I want to do a test, okay? I must have option value, okay? So internally, I use 30%, 0.3 as my volatility and use this number with the Black-Scholes formula to generate the option value, V here, okay? So that means the ground truth for me, sigma true is 30%, 0.3. I use this number, I use the Black-Scholes formula, I generate this is the option quote. Okay, now we pretend this is the option quote we observed from the market. Okay, so I myself know how did I get this option value. I used volatility 30% as my volatility. Okay, now once I get the option value, I want to test my Newton method. I want to see whether my Newton method can help me find approximation close to 30%. Essentially, I want to test whether my Newton method works or not. Okay, so here is the Newton method. Sigma hat is this my initial guess. Okay. Essentially, this sigma hat will be our initial guess. We use this one. So the first step, I calculate sigma hat. Okay. Then I set my tolerance to minus 10 to the minus 8. And the maximum number of iteration is 100. And sigma diff is 1. And n is 1. Sigma is sigma hat. So while sigma diff is greater than tolerance, and the number of iteration is less than 100, I'll continue to do the iteration here. Okay? See, first of all, given the current initial guess, sigma, right? Sigma hat is my initial guess. Sigma here equals sigma hat. So I plug into this initial guess into the Black-Scholes formula. I get the current value, C, based on the current approximation, sigma. Then I calculate the sigma vega. Vega essentially just the first derivative, okay? Essentially f prime sigma here, okay? That's called the vega here. So I calculate the option value, I calculate the current derivative at this sigma, okay? Then I calculate the increment. You see, the adjustment to the current approximation increment essentially just this term. It's just this term. It's just this term, okay? Fxn divided by x prime xn. Okay, this I call this term adjustment or increment. Okay, this is the increment term. Now we go back to the implementation here. See, C is the current option value with the current volatility approximation. C true, this is the option value we observed from the market, which is this one, okay? So the numerator here, this is just the nonlinear function fx, and this is the derivative. So the increment will be the fxn divided by x prime xn, okay? So this is the increment term, which is this one. Okay? So current approximation minus this increment will become our approximation for next step. So now we update the current guess by this expression. Then the number is increased by 1. Then we calculate the sigma diff. Essentially, sigma diff here, just the magnitude of the adjustment from the current step. If this adjustment is too small already, is smaller than the given tolerance, then we just stop. So that means not much space or not much room to improve the accuracy, because the increment from the current iteration is too small. We don't bother with we don't bother with more iteration. We just stop, okay? Or we exceed the maximum number of iteration. We also stop. Then we print the implied volatility, the current, the final approximation for the implied volatility. You see, my piece of code here gives the implied volatility is this. Remember, the true volatility is 0.3, right? 30%. You see, it's really, really accurate. Okay? So that's it. So, as I said, in your assignment, pretty much you can just copy this piece of code, but you need to add the sanity checks at the very beginning and also in the end, or even in the middle. If in the middle, somehow you should check the sigma here. If it becomes negative, you should stop. Why? Because the sigma should never be negative. If it becomes negative, that means you already start to see oscillations in your Newton method iteration. There's something wrong with the Newton method. It's not converging, okay? Or here, finally when you get the sigma here, you should check C minus C true, whether it's close to 0 or not. If the difference, when you plug this sigma back to the the Black-Scholes formula and you get the option value, if it's far from the given market quote for this option, that means your volatility approximation is not accurate, actually didn't converge. It's wrong as well. Okay, so you need to add the sanity checks yourself. Okay, so now, this is the Newton method for implied volatility. So since this is part of the assignment, I hope you treat it seriously. Previously, this is appeared in the final exam. I'm not sure this year whether there will be, but I just let you know, you'll be asked to write by hand the code for calculating the implied volatility. You send this piece of code. I'm saying previously, I'm not saying this year, okay? But the idea is, for all the important implementations, because this is computer science course, right? So for all the important implementations, if you have done it in your assignment, you should prepare, you'll be asked in the final exam. Okay? So this is the implementation of Newton-Raphson method for implied volatility. Let's talk about the implied volatility surface slightly. Okay, so the implied volatility from a call and a put with the same strike and the same maturity on the same asset should be the same. Okay? Does anybody know why? Why the volatility, the implied volatility from a call and a put with the same strike, same maturity on the same other asset should be the same? What if they are different? If you calculate the implied volatility from the call and put with the same strike, same maturity, same underlying asset, and they're different, very different, what does that mean? Which arbitrage? I think you're close. Yes, arbitrage. But in what sense? The put call parity. That means the call and put must violate the put call parity. Why? If you remember, C minus P equals S minus K times e to the RT. Okay, so the left-hand side is call minus put. The right-hand side is stock, current spot level minus K times e to the minus RT. You see, the left-hand side and right-hand side, they must equal to each other. But the right-hand side, when you take derivative with respect to volatility, is 0 because the right-hand side doesn't depend on any volatility. There's no volatility term at all. So when you take derivative on the left-hand side, the partial C, the derivative partial sigma has to equal partial P, partial sigma. So that means the sensitivity of the call must equal to the sensitivity of the put with reps to call to volatility. So that means they must equal to each other. When you take, so that means The call and put should have the same sensitivity with respect to volatility. So that means when you calculate the implied volatility, they must have the same implied volatility. Otherwise, it implies there are arbitrage opportunities. Okay? In practice, the implied volatilities from option, I think we talk about this, okay? From options on the same underlying asset, but with different strike and different maturity are different. You may ask why. This is not easy to understand as well, because if you think about it, they are on the same line, same underlying asset, but they have the same. They have different maturity. They have different strike. Why they have different implied volatility? If you are talking about the same underlying asset, they should have because intuitively volatility is a term that describes how volatile the asset is. So supposedly they should have the same volatility. Okay? But if you recall, previously I mentioned how the market forms consensus on the market quote on options. The first thing I mentioned is the option quotes coming from supply and demand, right? So different options coming from different supply and demand, then it leads to different implied volatility. For example, if the market, everybody rushes to buy the short-term options. Why? Because the short-term, there is earning report. The short-term, there's earning report. There is huge uncertainty around this earning report. So everybody wants to buy options to hedge their risk. So the option becomes more expensive, right? But nobody will bother with the long-term options because it's too far away. I don't care. I only care the earning report will happen next month. I only care about options short-term, let's say just 1 month's time. Okay, I want to buy an option to hedge the short-term risk. In that case, everybody want to buy, the whole market tend to buy the short-term option, will push up the price, right? Everybody rush to buy, then push up the price. So relatively speaking, it push up the implied volatility. Since nobody cares about the 1 year option, so it doesn't change at all. So the option price will stay as where it is. So relatively speaking, the implied volatility of the 1 year option, even though it's the same underlying asset but just different maturity, then that quote will relatively cheap, and the implied volatility will relatively cheap as well. You see here, this is a typical example of supply and demand change the relative richness or cheapness of implied volatilities. Okay? So that's why the implied volatility for different options with different strike, even though they are on the same underlying asset, different strike, different maturity, they're different. Okay? Strictly speaking, the only constraint of the non-arbitrary conditions we mentioned in assignment in assignment 1. So that means option prices, whether they have arbitrary opportunity or not, the constraints we prove in the first assignment are the necessary conditions. As long as the option prices don't violate those conditions, there are no arbitrary opportunities. Okay, so that means for option prices, there's a wide range, okay, that are feasible. Okay. So that's why for option prices, we subject to supply demand which leads to different implied vol numbers. Okay. So if we plot, so here, one more thing I want to mention. In general, the out-of-money option put have higher implied volatilities. Okay, why is that? We can talk about that quickly. So if we plot the implied volatility against the option strikes, we see a skewed curve and closely related to the option market crash in 1987. Okay. You see here, this is a plot I got it from some textbook. Okay, so the SP 500 implied volatility curve pre and post 1987. So pre-October 1987 is quite flat. Actually, from here, because I didn't generate this plot myself, I just copied from textbook. So it appears not that flat. Actually, it's quite flat. It just, the scale is an issue of scaling. It's quite flat. I think it's just it's less, roughly just 1% difference, I guess. So it's quite flat. But after that, you will see that the dip, the out-of-money put side. So this is the strike level. Okay, this is strike, not spot. Okay, this is strike. So for deep out-of-money put side, the implied volatility is really, really high, much higher than the rest of strikes. Okay, so why is that? It's just a little bit of background. This is for your information only. So the Black Monday of October 19th, 1987. So what happened on that day? So Wednesday, October 14th, the Dow Jones Index average index dropped 95 points. Okay, about 4% down. Then the Thursday, October 15, the Dow Jones down another 48 points. Okay, so that means, so back then, the Dow Jones Index is just the major market index, okay, for US market. Then on Friday, October 16, the Dow Jones Index down 108 points on record volume. Everybody is screaming to sell. And on the Monday of October 19th, the Hong Kong Hang Seng Index down 11%. The London Financial Times 30 Index falls 10%. You see here, this is a major market index. Okay, the large cap stock index. Okay, if this large cap index falls by 10%, you can expect the mid cap, the small cap in the stocks will drop even more, right? And the Dow Jones dropped 508 points, down 22% on record volume. On the Tuesday of October 20th, no bid. No one is buying. No one was buying initially. So you can Google the market crash in 1987 to read more about this. Okay, so after this crash, people realized that it's not rare that the market crashes. I mean, the market is down 10%. Before this 1987 crash, everyone thinks it's impossible. That means market cannot drop that much within a day. It's for Dow Jones is down 22% within a day, and several days in a row, right? So everybody want to buy insurance because people suddenly realize that, oh, it's not rare that the market crashes. So everybody want to buy put, deep automate put as an insurance, just to protect themselves in case the market crashes. At the same time, so because everybody want to buy such insurance, because first of all, deep automate put originally is really, really cheap, right? Was really, really cheap. Now everybody want to buy insurance by taking long positions on deep automate put. They push up relatively the deep out money put prices, right? Everybody want to buy, so want to buy the deep out money put. So relatively speaking, they push up the price. Nobody wants to buy the deep money call, right? If the market is skyrocketing, it goes up by 22% in a day, everybody is happy. Who cares? Who cares about the possibility that it goes up 20%? Everybody happy in that case. Nobody want to, oh, I want to hedge. I want to bet. That's not the case. On the other hand, the market crash is a real risk for everybody, right? In that case, maybe everybody wants to buy a bit insurance by loading long position in the out money put. So relatively speaking, they push up the out money put prices. Accordingly, they push up the implied volatility for out money put. This is one reason. Second reason is that for market makers, for example, investment bank, they don't want to sell the out money put too cheap. They don't want to sell out money put too cheap because it's a real risk. Market could crash. If everybody wants to buy an option out money put from you, you simply don't want to sell it too cheap because it's a real risk. When you sell it, you are putting on some risk. Okay, so you want to sell it more reasonably high price. That means you want to ask for higher premium for out money put. So it also push up the option out money put premium. Subsequently, you push up the implied volatility for deep money put. So that's why since the 1987 crash, the implied volatility becomes this shape. Okay. This is a plot from my previous work. Okay, I was dealing with the A50 ETF listed option in Shanghai Stock Exchange. So back to then, I have to explain. First of all, you may ask me why this is not the similar shape as I shown here. So that means the put side is much higher and the call side is much lower. So first of all, this is 8 years ago when 9 years ago when the A50 ETF just launched. So back to then, there are not many quotes for different strikes. Okay, so the strikes on the call side. So the put side doesn't have enough quotes. Okay, enough strikes. So I'm pretty sure if the put side have more strikes, it's going to go up like this. Okay. But either way, what I'm trying to say here is it's not a flat curve. Okay, it's a skewed curve. Okay, most of the time, this is a plot from a test book. So most of the time, you will see the implied volatility surface look like this. Okay, so this side is the deep money put side. Okay, it's this skewed shape, skewed curve, and also this is the time step. You see, when the time to maturity is shorter, at the money at the money area, the employee volatility is lower. Then the further away from the maturity, then it's getting higher and higher. But for the put side, when you're further away from current time, that means you're getting longer time to maturity. Actually, the implied volatility for put getting smaller. Okay, so this is this is a very typical implied volatility surface for stocks. Okay, so most of the investment banks they maintain such implied vol surface. They refresh this implied vol surface at least twice a day. At the market open, then before the market close. Okay, they maintain this implied volatility surface. Okay. A state-of-the-art technique for implied volatility. So the Newton method, even though in this course we discussed Newton method, and in the assignment we'll ask you to use Newton method, but actually in practice, if you find a job in investment bank, nobody use Newton method anymore. The reason being, the new techniques showed up about 10 years ago. Okay. No, actually not 10 years ago. 2000. Yeah. It's 10 years ago. Now, two papers written by Peter Jackal. He's I'm not sure what he's doing right now, but 10 years ago, he was a very famous quant in quantum finance. He wrote a book about Monte Carlo simulation method for option pricing. That's the classic book on this topic. We're going to talk about Monte Carlo method next week. So we'll talk about his book again. He's very famous and he's a very smart guy. So he wrote two papers. Essentially, the first one is B implication, okay? And then the second one is let be rational. I think now, before I left the investment bank, we are using the first, let's be rational, okay? So Peter Jackal on his website, he provide open source implementation of this algorithm for solving implied volatilities. Okay, it's very fast. You don't have to do yourself. You just pull out his code and then plug it into your inside your code. Then you can run it right away. I implement myself using the let be rational. It's very fast. It's guaranteed. Then you can get the implied volatility within 3 iterations. Okay. And the accuracy is up to the double, essentially the double epsilon, essentially 10 to the minus 16. Okay? So it's very fast and accurate. So most of the time now people just using this one. But the derivation behind Peter Jackal's algorithm is too complicated, to be honest. He applied many fancy, sophisticated approximations. So I thought about whether we should present his simple, but I realized it takes too much time to explain the idea behind it. So I just leave it for information only. If you want to give it a try, you can do it. But since it already has the open source implementation, you don't really need to do it yourself. But just for information. I think, let me see whether we want to start with. I think we only have about 6 minutes. Probably should stop here because if we start to talk about the option valuation with Monte Carlo, then we have to maybe just go for 2 or 3 slides, then we'll just stop. So let's call it a day. We stop here and we leave a bit early today. If you have any question, you can come to ask me. I'll stay here for a few minutes. Then let's just stop here. Have a good Chinese New Year holiday. If you have any questions, send me emails, okay? Thank you very much.